Of course, hocam.
Okay. All right. So let's continue kind of what we were talking about. So now what we're actually going to do is we're going to try to build a model that will give us expectations for summarizing DNA variation across a genome. And the way we're going to actually do this is by calculating something different. So we're going to try to solve a problem which is expected time to most recent common ancestor of 2 gene copies. So we're trying to kind of solve this problem, and this will be kind of our first this will be the first step in building a fully building the Coalescent model or the Coalescent theory, which will help us in predicting these predicting genomic variation across our DNA. So again, I'll explain what time to most recent common ancestor actually means. So again, when we're actually trying to build predictions, we actually need a basic model, right? For example, Heidi-Weinberg is a model with basic assumptions. And here we'll kind of be doing the same thing. So we'll be working with a basic model. And what we'll actually be doing is we'll be working with a Wright-Fischer population, okay? So everything that we kind of talk about kind of in these lectures will actually be based on a Wright-Fischer population. So what is a Wright-Fischer population for those who actually don't know? So a Wright-Fischer population is kind of very similar to kind of the Heidi-Weinberg equilibrium, which means in a population where we have constant population size. Okay, we have no selection and no kind of migration and equal kind of reproduction. Okay, so this is kind of like the basics of a Wright-Fischer model. So what does that actually mean? So let's just tell it with an example. Let's say we have a population that is made out of, let's say, 1, 2, 3, 4, 5, 6, 7, like 8 gene copies. So what a Wright-Fischer, kind of model predicts is it says that so each of these gene copies, so these are DNA copies. You can think of them as gene copies, DNA copies. So we have 8 DNA copies. Each of these will, produce the same amount of, so these will all replicate. And let's say this produces 2 gene copies. This produces 2 gene copies. This produces 2 gene copies. This one. So each of them produce, 2 gene copies for the next generation. They replicate and they produce 2 gene copies. Now, what the Wright-Fischer kind of model says is when we're moving to the next generation, the next generation of gene copies will be a random draw of 8 gene copies from this new pool of replicates. Again, so it will be a random draw. There's no bias towards one gene copy. One gene copy isn't like advantageous to another. It's just random draw of 8. So we'll be just randomly, let's say we're picking this one, picking this one, picking this one, picking this and this. 1, 2, 3, 4, 5, 6, 7, and 8. So we're randomly going to pick 8 of these gene copies and move them to the next kind of generation, okay? So this is in a nutshell, the Wright-Fischer kind of, population model. So we again have a new population, 1, 2, 3, 4, 5, 6, 7, I think that's 8, right? That's 8. So again, we started with 8, gene copies. We have a new population, which is again 8 gene copies. So there's constant size. There is no migration. We don't have migration in or migration out. So we're not losing gene copies. And again, each of these gene copies have descended from the gene copies in the previous population. And it's just, we've randomly selected any 8 gene copies from this new pool of 1. So there's no advantage. So this is basically a Wright-Fischer population. So it's a population with constant population size, no selection, no migration, and equal reproduction between any kind of gene copy. And any gene copy has the same amount of chance of being represented in the new population as anyone's here. Okay, so that's kind of like a basic Wright-Fischer population, which we'll be talking about. All right. Okay, so So that's kind of like the basis of the Wright-Fisher population that we'll constantly be talking about. But now let's go back to kind of our problem. Let's say we have a population. Let's have a population with 1, 2, 3, 4, 5, and let's say 6 gene copies, okay? And the question that we're actually asking here is, so we have this population of 6 gene copies, and the question is, how many differences do we expect between random pair of gene copies, okay? So this is the question we're trying to answer. So basically, if I pick 2 gene copies from here, any 2 gene copies, what's the expected number of differences between them? What kind of a difference would I expect between these between these 2 gene copies? Okay. So again, remember that's kind of the definition of pi. So we were talking about pi. Remember, average nucleotide differences between pairs of gene copies. And now we're kind of asking that question in reverse. If I were to grab, let's say, 2 of these gene copies, if I were to grab this one, and then let's say I was to grab this one here. So if I were to grab 2 of these gene copies, what's the number of differences that I would expect between them? Now, there's a lot of factors that go into that, okay? So let's think about some of the factors that might influence that. Now, one major factor is that since these are gene copies, they will have descended from other gene copies in the previous generations. So if we go far back enough, we're going to find an ancestor of both of these gene copies. So we're going to find a common ancestor for them. And the amount of genetic variation between these 2 gene copies will really depend a lot on when that timing was. So when the last time that these 2 gene copies actually shared an ancestor. If that was really far back, this means that these 2 gene copies have been separated for a very long time. So that will allow more and more mutations to accumulate, so differences will be larger. But if the common ancestor of these 2 gene copies is more recent, that means they'll have less time for accumulating mutations, so perhaps differences between them will be less. So again, a good question is to ask is between these 2, what is the timing of their kind of last or most recent common ancestor, okay? So that's one question we're asking here. So we're asking kind of the question of, when was the last time that these 2 gene copies had a common ancestor? And that's kind of so that goes back to here, most recent common ancestor. Why are we talking about the most recent common ancestor? Because again, since these are gene copies, once they find their common ancestor, then that gene copy will have a common ancestor with other gene copies, and it will just go back all the way to the beginning of life. But we're only interested in the most recent common ancestor because in the most recent common ancestor, these 2 gene copies were the same gene copy. So they were the same DNA copy, but then replicated and they became separate DNA copies. So that's why we're only interested in their most recent common ancestor, because that's when variation between these 2 gene copies did not exist. They were the same DNA strand, or they were the same DNA molecule, but then they got separated. So again, kind of predicting the differences between them, expected differences between them, depends a lot about us being able to figure out, when they had a most common ancestor and how long has it been since these 2 gene copies have diverged from their common ancestor. And so let's try to think about this. And since we're talking about a Wright-Fisher model, we know that, we can say that this is time t. So we can say that this is, we're at time t here. We know that, for example, at time t minus 1, there was, again, 6 gene copies in the population. Remember, this is a Wright-Fisher model. So, population size is going to be constant. And, sometime back, t minus 2 generations, there was another population that had like 6 gene copies, 1, 2, 3, 4, 5, 6 gene copies. That's T2. Then we can just like go dot, dot, dot. We can go back to like, specified time T minus, let's say I, T minus I, there's again 1, 2, 3, 4, 5, 6. So 6 gene copies. So this is kind of how we could, do these things. Like that. So, okay. So again, we can build this thing. So we can just keep on going back. And as we go back, we're going to have other populations with 6 gene copies. And we know that all of these gene copies descended from these gene copies here. All of these gene copies descended from gene copies at this generation and going back all the way. Now, so let's try to figure out, the timing of the most common ancestor of these populations. Now, how can we do that? So let's start with this one. So let's ignore this one, and let's say we picked this gene here. Now, we know that this gene descended from a certain individual. There's no question there, right? If we have this gene here, we know that it descended from a specific gene from this population and a gene from this population. They have to have an ancestor. They can't just come out of thin air. So it just makes sense that if we choose this, let's say this individual descended from this gene copy here. Then again, if we take this back, we know that this, for example, gene could have descended from this gene copy here. And we can take it all the way back to the most common ancestor. But the question here is, this isn't like anything debatable. If we have a gene copy, it's going to have an ancestor in the previous generation, it's going to have an ancestor in that generation, all the way going back. There's going to be that chain. And the question really starts is, well, if I take another, so I've taken this individual and there's no obscurity there. When I take this individual, what's the probability that this individual and this one come from the same, or a copy of the same gene copy? So what's the probability that this gene copy here came from this exact same one? Well, we can actually calculate this, right? So we can write this down. We can say probability most recent common ancestor at T minus 1 of them being the same. So what's the probability that this gene copy arose from this exact gene copy? So the same ancestor as that other gene copy. What do you think the answer to that is? So it's 1/6. Why is it 1/6? So we have 1, 2, 3, 4, 5, 6 copies in the previous generation. And when you actually look at it, we don't have any bias. This gene copy could have descended from this gene copy. This could have descended from this one, this one, this one. It could have descended from any one of these. So, the probability that descended from this same gene copy as that other individual or other gene copy is 1/6. It has, 1/6 of a chance of being descended from this, okay? So the probability that their most recent common ancestor of these two gene copies is one generation back in the past, so we can call these generations. So, we can say this as generations. So one generation, T minus 1 generation, so one generation back in the past is 1/6, okay? Is that clear? Do I have anything in the chat? I think there's one thing in the chat. Yeah, 1/6, yes, again. Sorry, I didn't check the chat. Yes, exactly, it's 1/6, okay? So that's very simple logic. But let's move further. It doesn't actually have to happen that way. So this would mean that, anyone of this gene copy has 1/6 probability of actually, having a common ancestor, this one generation in the past. We could actually do something similar. We can say, what's the probability that their most common recent ancestor is in this second generation? So it's not one generation in the past, but it's 2 generations in the past. Now, let's think of the amount, like the events that actually have to happen for these 2 gene copies to have a most recent common ancestor 2 generations in the past. Well, it has to not have a common ancestor in this generation. So what is the probability of that? The probability that it has a common ancestor is 1/6. So the probability that doesn't have a common ancestor here is going to be 5 out of 6, or let me just be consistent, 5 out of 6. So we don't have a common ancestor here. It could be this one, this one, this one, it doesn't really matter. But then in this generation, it's going to find its common ancestor. So it's going to be this one. So again, so here we're here. So what's the probability that, let's say it was this one, let's say kind of, its ancestor was this one here. So what's the probability that this one is, descends from this gene copy here? So, we're back to the most recent common ancestor. Again, it's 1/6, right? So the probability that it will, have a common ancestor with this one is 1/6. So that's 1/6, okay? So again, this is kind of the way that we can do this. And we can extend this logic to say, let's say most recent common ancestor, 3 generations back. Again, it's the same. So in the first generation, I'm not going to have a common ancestor. Then in the second generation, I'm again not going to have a common ancestor. And in the third generation, I'm going to have a common ancestor. So again, for T, for finding a most recent common ancestor in the 3 generations back in the past, I would have to do this. So I can actually simplify that, and I can say, so that probability is squared times 1/6, okay? And we can actually take this, all the way down. So we can say, dot, 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 we can say probability of most recent common ancestor is equal to T minus I, some unspecified time way back in the past. So this would be, 5/6 I minus 1 times 1/6, okay? So this is kind of like how generally we would look. So we could take this logic all the way back to an unspecified time to actually find, the probability that these 2 gene copies, shared a common ancestor any given time frame, okay? So what is this? So this here is a distribution. So this is a probability distribution. Okay, so now what we've actually done is we've built a probability distribution that actually allows us to calculate, for each specific time, what the probability is that these 2 gene copies will actually have shared a common ancestor. But so what do we want to actually calculate? Okay, and this is a probability distribution. Since this is a probability distribution, let me just do this. So since this is a probability distribution, if you take this to infinity, so all possibilities, so if we're going to the limit and starting from 1, this would be 1 minus p, let me just write this in, I minus 1 times p, this would be equal to 1. Since this is a probability distribution, if you add up all possible probabilities, we're going to converge to 1. And again, this p here is the probability that the event will happen. So this p here, so I've said probability is this one, okay? So this is actually p. Why is 1/6 p? Because that's the probability of the event we're waiting for. So the event we're waiting for is common ancestry. And we know that in each actual generation, the probability of common ancestry is 1/6. That never changes. Here, the probability that these 2 will have a common ancestor 1 generation past is 1/6. Again, here it's 1/6. So this is the probability, this is the event we're waiting for. So we can actually summarize this probability distribution, very simply as this. So this is, we're going to wait some amount of time when it's not going to happen, I minus 1 of the time. So it's not going to find the common ancestor, not going to find the common ancestor, not going to find the common ancestor, and then it's going to. So this is just the general way of writing, this probability distribution here. But what we're actually interested in this case is, let me just erase that so I have more space, RCA. So what we're actually interested in this case is, of course, the expected time, right? Expected time to most recent common ancestor. So this is a probability distribution, but what we're actually interested in is the expectation. So if I have this probability distribution, what is my expectation? So basically, what is my mean? An expectation in statistics is just basically a mean. So if I figure out the mean of this distribution, I would have my expectation to most recent common ancestor. So given all of these probabilities, and given this probability distribution, what is the mean time to most recent common ancestry, okay? And so that just means, so if I go MRCA, so that just basically means summing up, all probabilities all of the probabilities of MRCA at each time frame, and timing it by the number of events. So basically what this actually means is, for me to reach the most recent common ancestor at this time, one event has to happen. But if I actually want to reach common ancestry at generation 2, 2 events have to happen. So I have to times this by 2. Here, 3 events must happen. So I must times this by 3. Here, I events must happen. So I have to times this by I. So if I just multiply each of these probabilities by the amount of events that have to happen for that probability to come about, I can actually take the mean. Okay, so basically mean is timing it by the amount of events that have to happen for that probability and then summing them up. So this is exactly what we're talking about here. And so if we were to write this down, so if we go here and let's just write this down. So in this case, it would be all the way to infinity, starting from 1 to 5 over 6, I minus 1 times 1 over 6, times I. Okay, so this would give me the mean of this. So how do we solve for this? So if we solve for this, what do we actually get? Okay, so what's my expected time? Now, for those who know statistics, this actually here, what we're actually looking at is the geometric distribution. So if we were to look at this, you would actually see that this here and this distribution here is actually the geometric distribution. And we actually know the mean of the geometric distribution, the mean of the geometric distribution. So if we're calculating a mean for this, so we can say, expected time to most recent common ancestor is equal to 1 over p, okay? Or in our case, 6, okay? So this actually tells us that if we were to do this, we would have, so the mean waiting time, when we have a population of 6 individuals, the mean time that we have to wait, or in generations, number of generations we have to go back to have a common ancestor is actually 6, or the inverse of the probability that those 2 gene copies will share a common ancestor 1 generation in the past. So again, we can look and see that the probability that any 2 gene copies in this population will share a common ancestor in the previous population is 1 over 6. And the inverse of that is our expected time to most recent common ancestor. So if we were to solve this equation here, this geometric distribution, and take the mean of it, the mean would round out to 6 because we have 6 gene copies, and the probability that any of these 2 gene copies will have a common ancestor 1 generation in the past is 1 over 6. And the expectation or the mean of that is actually just the inverse of this probability, the inverse of the probability that any 2 gene copies here will have a most recent common ancestor 1 generation in the past. But let's do something else. So again, you could take this from again, we know that if we have a geometric distribution, the mean of that geometric distribution is the probability, the inverse of the probability of the event we're waiting for. In this case, it's 1 over 6. So the expected time to a most common ancestor is 6. So this actually tells us that it will on average take 6 generations for any 2 gene copies here to have a common ancestor. But let's, in typical kind of biological, biologist fashion, let's prove that. So it's not really hard to prove that the mean of this distribution is actually 6. So we could prove it mathematically, but again, I'm not a mathematician. So what we're actually going to do is we're going to prove it by simulation. So we're going to simulate kind of a game here, okay? So we can actually think of this, and again, yeah, let me just very quickly share my screen with you guys. So let's go. Okay, so let's play a little game. I'm not sharing my screen, I think. Let me just do that very quickly. Can I share my screen? Here we go. Okay, so let's go to Google Dice and let's try to kind of simulate this process with a die roll. So what I'm actually going to do now is let's number these, okay? So I hope you can still see the screen. Can you see the screen? So I'm going to number this 1, 2, 3, 4, 5, 6, okay?
Hocam, it is not clear now.
Wait, let me just stop sharing and let's do something like that.
Yes.
Okay, So I can actually number these gene copies from 1 to 6, just like a die. And I can say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 1, 2, 3, 4, 5, 6. So I'm basically numbering. So if we're going to simulate this process with a die roll, we can think of this as 1. And if we follow the ancestor of this one, this is again 1, this is again 1, this is again 1. And so the question we're asking is if we grab this individual here, and let's simulate this with a die roll. So I roll my die, and if it comes 1, in the first try, that means, we find the common ancestor in one generation. I throw it again, let's just do this with a die. So each time, so the die, if I'm able to throw 1 with a die, it means that, we found our common kind of ancestor, and we're going to see, how many tries it takes us to reach that number 1, and that will tell us how many generations back we have to go to actually find our common ancestor. So now let me reshare my screen. Let's share the screen. So here we have a dice, and let's roll it. So we rolled it, and it's 6. So again, in this case, we rolled it once, and we haven't found our common ancestor. So let's roll it again, and it's 3. So we've rolled it twice, and we haven't found a common ancestor. I said, let's roll it again. We've rolled it 3 times, again, didn't come up with a common ancestor. We folded 4 times, didn't come up with a common ancestor. We rolled it, the 5th time, again, no common ancestor. 6th time, no common ancestor. 7th time, no common ancestor. 8th time, no common ancestor. That's taking a very long time. 9, 10, 11. This is really funny because why am I not seeing 1? 12, 13, 14, 15, 16. This is really funny. 17, 18, 19, 20. The odds of this happening is really, really low. So I'm wondering if there's something wrong here. Okay, it shouldn't really take this long. Wait, what's going on? No. What can I, again, this is ridiculous. Okay. Okay, there we go. So that took us about, I think, 17 tries to reach 1. So in this case, it took us like approximately 17 generations to reach a common ancestor. But we could do this again. So we're looking for the mean, right? So we can repeat this process again. So we can try again. That's 1 generation, that's 2 generations, that's 3 generations, that's 4, 5, 6, 7, 8, 9, 10, oh my God, 11, 12, 13. So this time it took us 13 generations. So in the first one, it took us about 17 generations. Now it took us 13 generations. And we can repeat this process, a third time. That's 4 rolls. That's 5 rolls. Now it took us 6 rolls. Okay, so this time it took us 6 rolls. So in the first one, it took us 17, the other one 13, and this time 6, just 6 events. So again, what we talk about the mean of this, all we have to do is take the mean of these trials. But of course, we should try this more than once. So we can actually do this event 100 times. We can roll this die 100 times and try to calculate, how many rolls of a dice it takes us to reach 1 in each of those 100. So, instead of doing this one by one like this, what we can actually do is we can do a simulation. And I've, done that simulation here. So let's look at kind of a simulation. Let's simulate this using a, simple R code. So what we can actually do is we can, simulate this exact event. So we're going to have 100 trials. We're going to roll a dice 100 times. And each time we're going to kind of calculate how many times we had to roll that die to get a 1. If we get a 1, that's completion of our event. Then we're going to do that again and see how many tries it takes us to do 1. And let's kind of look at, what that actually looks like. And then we're going to draw a histogram to see how that looks like. So let's do this with 100 tries. So again, what we've actually done is we've thrown a dice 100 times. And as you can see, 25 of the time it took us 1 try, 16 of the time it took us 2 tries, 10, it took us 10 times it took us 3 tries, and vice versa. So this is the number of trials. So basically, 25 times it took us 1. And again, as you can see, this is like a sloping distribution. And then we could go ahead and calculate the mean of this. And how would we calculate the mean of such a distribution? Well, it's very simple. We had 1 25 times, so 25 times 1. 25 times 1, we had 2 16 times, so 16 times 2 plus 25, then 10 times 3 plus all of these, and then just take the average, so that would be 100. Okay, but we could actually do it very simply in R. So let's take the mean of this and let's look at the mean. So the mean is 635, and as you can see, again, we're very close to our number there, 6, which the geometric distribution tells us that the probability that any of those gene copies will, find a common ancestor, the average waiting time for a common ancestor, or the average time that any 2 gene copies in a population with 6 gene copies is actually 6 generations. So it's the number of gene copies. Okay, and we could actually show that, this is 6.35, but as we actually increase the number of, what will actually happen is let's increase the number of trials. Okay, so let's say instead of 100 simulations, let's do 1,000 simulations. Then of course, again, and let's calculate the mean. So let's calculate the mean again, like that. And this time, as you can see, mean is 6.044. So what's actually happening is as we increase the number of trials, if we increase the number of that simulation, what we're actually going to do is we're going to start converging on the mean. So again, this is a very nice way of showing how the geometric distribution, again, the mean of the geometric distribution is just the inverse of the probability of the event you're waiting for. All right, and this kind of like nice die simulation actually proves that. So we have 6 sided die, we have 6 gene copies in the population, and this actually shows us the average waiting time for any of those 2 gene copies to coalesce is just the inverse of the number of gene copies. Okay, so it will take us on average 6 generations for any of those 2 gene copies to find their common ancestor. Okay, so so if we were to go kind of technical, so if we were to talk about this, so again, what we actually have is the mean is 6. So we can actually say that in this specific case, if we have, if we have a population with 6 gene copies, so if we have a population with 6 gene copies, the expected time, the expectation to most recent common ancestor of those gene copies is just going to be, the inverse of the probability of a most recent common ancestor, t minus 1 generation in the past. Okay, so again, if we have 6 gene copies, the expected time to a most recent common ancestor is just the inverse of the expected time to a common ancestor 1 generation in the past. And in this case, this is 1/6. So our expectation to a most recent common ancestor is just going to be 1/6, the inverse of 1/6. So this is going to be 6. And again, we just proved that with a basic, die simulation. But what does this tell us? This actually tells us, in generations. So this is in generations. So 6 generations. But this is, as you can see, also the number of gene copies. Okay, so this just basically means that the number of gene copies determines how, on average, how many generations we have to wait back to find a common ancestor between any 2 gene copies. Okay, so there's kind of a one-on-one correlation with the number of gene copies in a Wright-Fischer kind of model and the amount of generations it will take us to actually converge on the most recent common ancestor. Okay, so there's this nice link to it. But how can we actually use this? Okay, so let's see how much time I have. About 10 minutes. That's good. So let's actually write this in a more formal sense. So if we're actually trying to formalize this, we can say probability of most recent common ancestor at t, minus 1 is over 1 over 2n. Here we're talking about, let's say we have a population. So here we have n is number of individuals in a population. So 2n is equal to number of kind of gene copies, okay? So that's how we can write this nomenclature. So we can say that the probability that, given a population size of 2n, the probability that any of those gene copies will coalesce is 1 over 2n. And again, we can say probability of most recent common ancestor at times t2 is 1 minus 1 over 2n over, times 1 over 2n. And then we can, extrapolate this most recent common ancestor t minus 3 is equal to 1 minus 1 over 2n minus, times 2 times 1 over 2n. So again, if we go back to this kind of logic, we can actually see that we can say probability of most recent common ancestor at t minus I. This will give us 1 minus 1 over 2n over 1 minus I times 1 over 2n. Okay, so we can just instead of just building it, so I'm just going to erase this part here. Right here, like that. So if we follow this logic with just n's, we can actually see that we could just do the same thing. So again, we could, again, I'm usually, this is not, these are, so expected time to most recent common ancestor, this would be, just adding up over, I is equal to 1 to 1 minus 1 over 2n, I minus 1 times 1 over 2n times I. Okay, so this is just generalizing it. And if we go actually down here, this would tell us that, the expected time, so this would be expected time to most recent common ancestor, in this case, would just be the inverse of 1 over 2. So the probability takes me 1 generation to coalesce, so that would be, the inverse of 1 over 2, so that would be just 2n. So this is kind of the general formula. So basically the expected time to most recent common ancestor of any population is actually the number of gene copies. So, twice the population size or the number of gene copies in that population. And this is, of course, in generations. Okay, so roughly it will take me, the number of gene copies that I have is the amount of generations that will take any population for any two gene copies in the population to actually find their common ancestor. Now, what does this help us with? So remember, we were just doing all of this to understand something very specific. So we were trying to understand, the amount of differences between any gene copies. So we started this by saying, if I randomly select 2 gene copies, what's my expectation for the number of differences between them, right? And we know that the number of differences, average differences, between gene copies is high. That statistics that we talked about. So average differences between gene copies is pi. So I'm asking, what's my expectation if I pick 2 gene copies on random? What's the expectation of the differences between them? What on average do I expect? Well, we actually now know on average, if we pick 2 gene copies, they're going to have a common ancestor 2n generations back. Now, how can I use this? I can actually use this because if I look at these 2 gene copies, now I actually know the amount of time in generations that it takes for these to be a single gene copy. So I know that this time here is now 2n generations, right? It's 2n basically. 2n generations ago, these 2 populations or these 2 gene copies actually had a common ancestor. So let's say this is t, and this could be, t minus 2n. Now, what this also actually tells me is now I actually have a time in generations for the amount of time that mutations can accumulate. I know that within this 2n generation span, mutations could occur here, let's say, through that history of divergence, mutations accumulate here, but, mutations could also just similarly kind of start occurring on this branch as well. So there's two branches where mutations can actually occur. So if I want to actually calculate the difference, I have to kind of count the number of mutations occurring here and count the number of mutations occurring here. So let's drive an expectation for our differences. Okay, so expectations for differences. So what's my expectation for that? So that's time in generations. Okay, so time in generations. So that's one of my expectation. I'm going to, times 2, because I have one branch here, which is accumulating mutations, one branch here, which is accumulating mutations. Time, of course, the mutation rate, the probability that a mutation will occur. Mutation rate, okay? So this is kind of like how I can come up with an expectation for the amount of differences given this divergence. And we can actually, formalize this even more. So time in generations is 2n. We can write 2n here, times 2 times mu as the mutation rate. And if you actually look at this, we're back into this familiar, notion of 4n mu. So the expected number of differences between any two gene copies is actually 4n mu. So 4 times the number of individuals times the mutation rate, whatever actually the mutation rate is. Now, the last thing we're going to actually touch upon here is, so what does this give us? This gives us the expected differences. So if we have we have this formula now, which gives us the number of expected differences between any two individuals is 4n mu. But we also know how to calculate this, right? Average differences between any gene copies is actually pi. So this means that this 4n mu is actually equal to pi. So now we have an expectation for pi. Given a right Fischer model, we know what to expect. So pi is just going to be, 4 times the number of gene copies times the mutation rate. We can actually calculate pi, just from looking at these averages. But, right now what we've actually done is we've built a kind of predictive algorithm, and using our expectations of time to the most recent common ancestor and knowing something about how gene copies diverge, we've come up with an expectation for how much difference we should observe between any two gene copies. And that, this parameter here that we just, came up with in a total different way is actually exactly equal to pi, which we've actually calculated before. And so this is also known as, let me just do something here, just to finish off for now. So again, what this actually tells us is that that statistics pi is actually, equal to the expected differences. And it was Tajima who first thought of this. So Tajima, so this is also known as Tajima's estimator, or, theta t for Tajima, or theta pi. So this is that famous theta pi. So we actually know today that, theta is equal to 4n mu, and it's actually a very important genetic parameter, because it tells us the amount of genetic variation in a population has to do with, so it's the parameter that determines the amount of genetic variation. So the amount of genetic variation in a population has to do with the mutation rate and population size. And again, we can say that this is also equal to pi itself. What does this mean? So this means today in modern genomics, we can actually calculate pi, right? We did this together in the previous class. We calculated pi. So let's say we have an estimation of pi from our genetic data, which is 0.0333, per site. Okay. So this actually means that theta pi is equal to this. So this actually means that 4n mu is equal to this. So we can actually say, we can today just, grab random gene copies from our populations, calculate, pi, and then using this, we can actually equate it to 4 and mu, because we know that that's our expectation from the Wright-Fischer model. And if we have an estimate of the mutation rate, let's say it's 10 to the negative 8, then from here we can say 0.333 should be equal to 4n times 10 to the negative 8, and from here we could actually calculate population size. We can say the population size is 33 over 4 times 10 to the negative 8, which is equal to about 83,250. So what we can actually do is, we can just use this equivalency or expectation together with our measurement, which we can actually measure today, and for example, estimate population sizes of our population. So again, this is kind of like the first foray into how we can use coalescent theory to drive expectations for some of our statistics or summarizing DNA genetic variation. And here we've actually shown that we can come up with an expectation for the average differences between copies, and it tells us that that expectation is the number of generations. The number of generations, or the number of gene copies, actually determines how far back we have to go to find a common ancestor, and that determines how much genetic variation we're going to actually see in our population. And we can equate that to our nice summary statistics of pi. So now we actually have an expectation for pi so that we can use it to calculate such parameters as population size and whatnot, and we'll talk more about them in tomorrow's lectures. Okay, so thank you for listening. Are there any questions? If not, yeah. It might have taken about 10 more minutes of your time. Sorry for that. And tomorrow we'll try to be more punctual. Thank you.